Thanks for coming out on this nice, warm summer evening when you could be home watching baseball, I guess. And hopefully you enjoy this. I'm going to talk about wind research at Western. We've had some wind coming close to home here in London in the past few years. This summer, just end of August, we had the big tornado in Goderich. And you can see the damage that it wrought. And I'm going to talk a little bit about our work at Western, focusing on mitigating damage that occurs in tornadoes such as this, and a few other things that we're doing at Western with regard to wind. Well, we know the bad side of wind. We saw Goderich, but tornadoes can also be very, very beautiful. Does anyone know where this actually is? Have you seen this photograph before? I think it's both beautiful and a little bit frightening. If I was that close to take that photo, I'd be quite scared, actually. No one knows where that is? It's here in Canada. It was in Ely, Manitoba in 2007, and it was the first F5 tornado in Canadian history. Tornadoes are described by the damage that they cause, and F5 is the most destructive. When you hear on the radio that there's been a tornado and they give wind speeds, actually what's happened is we've looked at the damage, estimated what the damage actually was, and from that estimated what the wind speeds are. So the wind speeds that you hear on the radio are just good guesses, if you will. But we categorize tornadoes by the damage. So this photograph is quite a beautiful photograph of the tornado in Ely, but I'm going to show you the destruction that it wrought. So here's a video. It's probably a bit hard to see at the back. That just lifted there, that was a full two-story house that was lifted in the air. And in one moment here, you're going to see a van come flying out. It looked like a punted football. There it is right there. And it went about 300 yards. It was a van, a minivan, but it was full of construction materials, drywall basically, so it was extremely heavy, and it embedded in a farmer's field about 3 feet down, and apparently the headlights are still sitting in the dirt there a few years later. So that's the other side of this tornado. The other thing that kind of surprised me about that video, you see all the vehicles driving by and no one stopping and getting out of the way of what is the most destructive tornado in Canadian history, which occurred about 20 kilometers away from my childhood home, by the way. I'm going to take a step back and talk a little bit about the history of wind engineering, and then talk about where we're going and end up where we're going in the future. And so a little bit of a historical perspective. I think probably a lot of people in London have heard of Professor Alan Davenport, who founded our Boundary Layer Wind Tunnel Laboratory. He passed away a couple of years ago. This is a photograph of him in 1963 at the wind tunnel at Colorado State University, where they were, of course, testing the World Trade Center towers. At that point in time, there were no boundary layer wind tunnel laboratories anywhere in the world, and buildings such as the World Trade Center towers, if they got tested, were tested in aeronautical wind tunnels, which gives the wrong information. In fact, they're excessively conservative, so you couldn't have actually built structures like the World Trade Center towers without the modern wind tunnel testing that Professor Davenport developed. And so that's really where it all began. Apparently, this is 1963, after doing this testing, he went back to Western and talked to the president at the time. They had dinner, and he got $20,000 out of the president, and he built our first wind tunnel and a lab for all of that. I'm going to show you a little later on where we're going with the $30 million wind tunnel, so things have gotten more expensive over time. So this was the lab as it was in 1983 when the second wind tunnel was built. This was the original wind tunnel for the $20,000. It tested many of the world's premier high-rise structures. This is a photograph of Hong Kong. The Bank of China building is here. And I think it's the Shanghai Bank that's being tested in there. We have other features in the wind tunnel. I'm going to go over that really briefly. This is the Hibernia drilling platform, and in our wind tunnel we also have this wave generator, so wind and waves can be looked at simultaneously, and of course this is critical for drilling platforms. We know the destruction Hurricane Katrina wrought in New Orleans, but it also took out several oil platforms with 100-foot waves out in the Gulf, and so this is a significant issue for design for windstorms. And then our current wind tunnel from 1983, still state-of-the-art, showing some building testing. So we've been doing high-rise buildings for more than 40 years. It's still the state-of-the-art for design. In fact, one can't even really compute wind loads on structures yet at all. You can design an aircraft. The Boeing 777 Dreamliner was designed completely by computational methods, and then they tested it by measuring the gas mileage from flying from Seattle to LA. But the design of an aircraft, they put hundreds of millions of dollars in. Buildings, you can't afford to do that. And in fact, the aerodynamic problems for buildings is more complex because of all the turbulence in the wind. So the state of the art is still wind tunnel testing. And you can see when you have complex structures like this bridge in South Africa, the main span here is about 500 meters in full scale, and the canyon is about 250 meters deep. You can see the complex terrain. There's a large mountain here. Designing for the turbulent wind caused on that structure, you just can't do computationally. And we have been able to develop the wind tunnel testing methodology over this period. So this method is well established, and engineered structures like long-span bridges, high-rise buildings do very, very well in extreme windstorms. When hurricanes hit, they tend to do very, very well. What doesn't do well is houses. And so that's where we focused our effort over the last 10 or 15 years or so, and we've been working quite significantly on trying to mitigate damage to housing. So this is a photograph from the Barrie tornado. I'm going to come back to it a little later, but there's a bunch of aspects that we have to look at if we're going to stop damage to houses. First of all, after storms occur, we need to go and look and see what happened. And so we do damage surveys. We have a rapid response team. When there's a tornado, Environment Canada calls us. And we had a student with Environment Canada in Goderich 3 hours after the tornado, and they were looking at damage while the electrical lines are still live and stuff like that. And so we go out and we help them assess the damage by looking at the problems. They're experts in meteorology, of course, but when you look at damage, you need structural engineers, you need wind engineers to look at that. So we look at that and try to identify where problems are. Often in tornadoes, it looks like chaos, but after you've looked at a few of them and you start to see some repetitive patterns. I'm going to talk about that a little bit later in the talk. We also need to look at wind loads. So we need to do wind tunnel testing to understand the aerodynamic loads. We need to do structural testing to understand how houses respond. I'm going to talk more about that as well. But houses are more complex to understand structurally, to compute how the loads move through the structure than a high-rise building. It's more complex to design this house on a computer than it is the World Trade Center tower structure. Okay? And I'll talk about why that is in a minute. And then where we hope to impact is building codes. So normal homeowners will never see the kinds of things that we work on, but that's where we try to affect is how we build our houses and what goes into them. And of course, as homeowners, you pay for that, and so we're also sensitive to that. So what one wants to do is increase the resilience of the houses to these extremes while not making them cost more. That's the challenge. So we've been working in wind tunnels for a long time, and we can measure wind loads on houses using the same tools that we have. It's not as sexy to see a house in the wind tunnel as it is the World Trade Center towers, but we can use those same tools and we can work out the wind loads. Let's talk a little bit about those wind loads. So what I have here is just a large low-rise building. This could be a Walmart or an industrial warehouse, and we're just putting smoke in the corner. The wind's coming from a corner. We've painted the building black so you can see the smoke. And it's going to turn around here in a second. And what happens is that when the wind comes here and impinges on this corner, you see the strong swirling motion. That's a vortex. It's like a delta wing vortex on a fighter aircraft. In fact, the physics are the same. And you get very low pressures inside that vortex. You can see the intense swirling, and that causes very low pressure. It wants to lift the roof. Aircraft also, when they're speeding down the runway, they generate lift and they go into the air. When the wind blows over a house, you have the same physics. The wind speeds up and you have lift, and it's that lift that we need to work with as engineers. So that's what the wind looks like as it moves over a house. That may or may not be too important. What we care about are the forces. And so this is what the forces actually look like. So this is actually a house that I'm going to show later on. This is the Three Little Pigs house. The color contours are positive pressures, so pressures that are kind of close, not doing too much. It's the blue ones here that we're concerned with, and that's a lot of uplift. Okay? So this video is playing back really at real speed and at full scale speed. So what you can see is how fast the pressures are changing on the roof. And every once in a while there's going to be a very large hump of blue right there. okay, for a very short duration. And that's how the wind acts. So you have this wind, we can feel the turbulence when you're walking on the street. The same thing happens on the building. You have the turbulence, you have these vortices, and every once in a while you get a huge uplift for a short duration, and it wants to lift your roof into the air. Okay? Now there's no quizzes, but I want to make sure that this is perfectly understandable. So we have the big bad wolf. Now take your house, imagine turning it upside down. Don't just turn it upside down, let's hang some weights on the roof. Okay, and then let's start shaking the hell out of it. Okay, that's really what the wind is doing. Okay, so if you can picture that, then you can understand it. Now most people, when they think about their houses, builders, when they build their houses, think about holding the roof up because you don't want it to fall down on you. When the wind is coming, you want to hold the roof down. Okay, so the nails that are holding your roof down become really, really important. Little details become really, really important. Let's show some examples. So this is Ely, Manitoba, that F5 tornado, that house you saw flying through the air. That's really extreme. Okay? Now if you look at the picture, there's a car flipped over here. These people here, what are they doing? Well, this is the foundation of a house. They're looking down into the basement. The house is gone. Okay? There's actually, I heard on the radio, an interview after with a couple that were in this house, and they had taken shelter under a mattress, and they went to the basement, which is the right thing to do, got under a mattress, and apparently the wind lifted them up a few inches in the air and they fell back down, and then when they looked up, they just saw a blue sky, but they were okay. Amazingly, no one was killed in this event at all. So let's look closer at this house. Okay, the house is gone, that's bad. What I notice here, the first thing I notice, you see the cars flipped over, you see the mess, there's a beam here, so the people were quite lucky not to be injured. But there's nothing holding the house onto the foundation. So the weakest thing in this house was how the house was sitting on the foundation, and when a very strong wind came, it lifted it in the air and destroyed it. Okay? What should have been there? There should have been a bolt embedded into the concrete foundation. Here's the plate that the wall is sitting on. There's a washer there. That washer is really important. How much does a washer cost? I don't know, a penny? There's a nut. This is a proper foundation connection. If you do this, that house probably would have still been destroyed, but I bet you the floor would have remained because something else would have broken above it, and the people hiding in the basement then are much less at risk. So something like this can make a difference, and it can make a difference in terms of life safety. It's these little details that become really, really important. Well, in most windstorms, I'm going to show you lots of photos of roofs coming off. What holds your roof down in a windstorm? Well, let's look at into a roof. If you have a wood frame house, this is what it looks like inside your attic if you climb up there. So this is the top of the wall. This is a 2x4 right here. Okay, and this is actually a connection. So there's two nails here, and on the other side there's supposed to be one nail. So you have three nails going from the truss into the wall. And this is what holds your roof in place. Okay, it's those three little nails. The trusses are every 2 feet, and they're nailed like this. This was in our lab, so this was made by students at Fanshawe College. Is there any Fanshawe students here? One? Okay, I'll have to watch what I say. But you can see it took them a few tries to get it right, and they had to pull a few nails out, and the lumber's cracked. So this connection actually has no capacity whatsoever for uplift. It's entirely useless for wind. Okay? And I guarantee you if you look in your house, well, don't, because it'll probably depress you, but you'll probably see connections such as this. Okay? All right, so that's the standard thing. So a lot of what we're doing with is looking at nails. Okay? And you have this kind of variation, cracks in the lumber. Lumber dries out, there's cracks, there's knots, all sorts of things like that we have to deal with. In fact, that makes it very difficult to analyze structurally because I don't know what to do with that as a structural engineer in terms of design. When you pull the nails out, this is what it looks like. So you see the three nails, okay, and here's the top plate of the wall, and you can see what's holding the roof down. Okay, so that's one that we broke in the lab. So let's take a look at some failures. This is the most common, the most at-risk part of any house in a windstorm is the roof. So that's why I spend so much time talking about the roof. This is a photograph. Does anyone know where this one is? You're a very quiet group. This is Vaughn. Pretty good guess. It's Vaughn 2 years ago, 2009, when we had 19 tornadoes in southern Ontario in one day, and we had 2 in Vaughn. Okay, and so this was this neighborhood here. The tornadoes came during supper hour. No one was killed, and I think there weren't even significant injuries. This is it was an Italian neighborhood, and apparently they like to have their kitchens in the basement. I didn't know that. And so they were downstairs cooking. It was dinner time, and people were in their basements naturally. And apparently, so no one was hurt because of that. I think that's remarkable. I'm not sure entirely how true that is, but that's what several people told us when we were there the next morning. So you see the roof's gone. Okay, so let's take a closer look at some of those. This was a lovely, well-built house. Here you have, it's a block wall, so it's very, very, very strong, a house made of brick, if you will. But they put the roof down, and they did something that was better than code. They put the roof beams here every 12 inches. So if you have a big, huge snow load, this house is going to be just amazing. Okay? Unfortunately, the nice thing now with modern cameras with 16 megapixels is from the street, you can actually see if there was nails. And you can see that from here, the roof was just lying on the walls. So it had no connections whatsoever. Okay? So they lost their roof as a result of that. Okay? So this was an example again of, they put some effort. The house, look how tidy it is, the nice roses, but the nails were missing there. This was in a different neighborhood in Vaughan, and these were houses that were about 5 years old, and I think they were very, very well built. What happened here was, in storms, there's a lot of debris, and I'm going to talk about a lot of debris. So there's stuff flying around everywhere, and that's one of the reasons why you want to get into the basement or get as low as you can, is to get away from the debris. You can see there's a hole in the wall here. They had projectiles broke this window, and this caused the roof to fail. So what happens is, when the debris breaks your window, you basically puff up the house like a balloon. So you have the wind pushing in, pushing up on the roof, and then you have those low pressures from the vortices that I showed you before acting, and those two act together, and this is the cause of most roof failures. Okay, so debris is a really, really significant issue. These people lost their house because the front doors blew in. So what do you have holding your front door? A little tiny knob. The deadbolt wasn't closed, right? And the wind came. It was an open area from here, from this side, and the wind blew in and blew the doors in. And what happened is the roof blew off. And so that was the one problem. So they had this internal pressurization. And then when you look at the nails, they only tended to have 2 nails instead of the 3. So again, the capacity of the roof for resisting the wind was also much lower. So we have those two things acting together to cause a problem. This was the neighbor's house. Okay, this is the next day. I see a shingle off here, some damaged shingles here. There's some debris sitting on the roof, but they're okay. These houses were the same, so you can see exactly what was lost next door because of the door blowing in. Okay, little details. Nails. I showed you the nails going in and out and being removed and cracking trusses. Often when we look at after a storm, we go and actually count the nails. And ones like this nail didn't help at all because it wasn't touching the truss. So a nail that isn't in the truss has no capacity. What's worse than that is that nails that are on the edge of a truss have a little bit of capacity, but only a few pounds. And so nails on the edges, when you're right down the middle, they're pretty strong. When you're on the edge, like that one there, they also have very little capacity. So often when we look at sheathing afterwards, we see those problems. And so often, at least the first things that break in severe windstorms are often things that we could easily stop. Okay, so stuff breaks and then it flies around. And this is a photograph from Goderich. Bricks everywhere. It was a lovely old city made with lovely double brick walls, so a nice strong construction, but there was bricks everywhere afterwards. What happens to that when that fails? It flies around. You can see the bricks in the flower pots. You can see we saw bricks everywhere. So stuff breaks, it flies around. And it becomes dangerous. So it's like spears. I mean, you see these vehicles. This is the kind of thing you see all the time. 2x4s impaling different objects. I'm amazed no one was killed actually in the city. The one person that lost his life was in the salt mine. Okay, but it's a miracle that that no one else was hurt with you when you have this kind of stuff flying around. And the bricks, okay, here's a nice vehicle. You can see the brick in the window. The driver's side window is open. Actually, the driver's side window was broken by that brick. That brick broke the windshield from the inside. Okay, it broke it from the inside. So you don't want to be sitting in that driver's seat when that happens. So it's this kind of thing that is so devastating. So the more that we can keep the buildings together, the less debris there is going to be, the less follow-on damage. In hurricanes, debris is estimated to cause 40% of the damage. So that's a lot. In tornadoes, it's even higher. Here's one. These people left their garage door open. Well, so what? But again, the wind came, pressurized the roof lifted up, went away. The rest of the house looks fine, but their neighbors didn't do so well because the garage roof landed on their garage and part of their roof and caused this damage. And so stopping debris is a really important thing. We could probably have stopped that by using something called hurricane straps, which would have, for that garage, would have probably cost about $15. Okay, now all these things add up to the cost of a house, but we're not talking about a lot of money to mitigate wind damage in this particular case. My photo disappeared. Huh. All right, we'll skip it. When we have debris then, it can travel at high speeds. So let's say in Goderich we had wind speeds of 200 kilometers an hour. If a piece of plywood from your roof fails, okay, a 4 by 8 foot sheet of plywood, I've just shown how that comes off. Plywood can travel at about 70% of the wind speed that caused the failure. So 200 kilometer an hour winds, you can have plywood traveling at 140 kilometers an hour. Shingles can actually travel faster than the wind because they can generate so much lift and they're very, very light. And so around a roof where the shingle fails, they actually travel faster than the wind. So again, in that 200 kilometer hour wind, our wind tunnel studies have shown that they can travel 220, 230 kilometers an hour. And so a shingle, you don't think of it as being very heavy, but traveling at over 200 kilometers an hour, race car speeds, that's a little bit frightening. Again, it'll break a lot of things. What I want to show here is a wind tunnel study. This is from a hurricane. So tiles from this house failed and hit this house, and this house had no damage otherwise except for all these these tiles hitting it. This was in Florida. So we can actually do that in a wind tunnel. So we have a tile here. See if we can get this video going, and you're going to see it. Oh, it's not very happy with me today. You can see it there flying through the air. Okay, so it's bouncing off its own roof, flying through the air. And in a moment, we have two cameras. You're going to see it come over here. Hopefully it's going to play. And then you can see it hit there. Okay, so we can actually investigate these kinds of things. If there's a window there, that window is going to break, and then you have these problems with internal pressurization, and you may lose the roof as a result. All right, so debris is a significant issue. In lots of places, we use rocks on roofs to hold them down. So one of the most cheap forms of roofing for industrial buildings is they put a waterproof membrane and then they put rocks on top of that to hold it down. Now in a windstorm, that's not a very good idea. If you're a building owner, you like it because it's inexpensive and it's easy to repair, but you end up with rocks. So throwing rocks at windows isn't a good idea. We actually do tests on these kind of things to see what kind of wind speeds can cause rocks to become airborne and then determine whether they'll break windows at those speeds. And not surprisingly they do. And if you videotape at 8,000 frames a second, you can actually see how the rocks fail. One of the recommendations for tornadoes is not to stand by windows during the storm for exactly this reason. I don't know if you saw all the shards of glass going inwards, but that's exactly what happens during a storm. I'll play that again. You can see that. Boom, and you see the jet of glass coming out. In fact, the wind pressures, which will cause the window to deflect, can leave tiny shards off, and so you should not stand around windows in strong wind. in extreme wind. Well, that's I guess the scary kind of stuff that wind can do. Let's look at some of the positive things that we can do. So this is the Barrie tornado, 1985, so it's 25 years ago now. And this is a photograph I like to show. All these houses here, looks like chaos, the roof's gone. And these all, you don't know what's there, but if you look at photographs from before, these all had gable roofs. Gable roof's just a simple two-surface roof, the kind of roof that a child would draw. These houses back here, you think, okay, tornadoes have kind of erratic damage when you look at the patterns, but when you start digging in, you see maybe not. These all have hip roofs, and this photograph inspired Professor Davenport to actually do a wind tunnel study of houses. No one had done a wind tunnel study before that. And they actually showed that wind loads on hip roofs are a lot lower than on gable roofs. So they're more aerodynamic. And on top of that, they're actually structurally stronger because they have connections on all four walls, whereas a gable roof only has them along two walls. So basically, a hip roof house can withstand a 50% larger wind speed than a gable roof. Now, when you're thinking about buying your house, this is not something you think about, but if you're in a wind region, it's a significant issue because I'd rather be in that house. It's also one story, so it's lower to the ground than these two-story ones. That also helps. And it's stronger and more aerodynamic. And so it's a really natural way of mitigating wind loads. Talk about the height of a house. These are pressure coefficients. The blue colors, again, are the uplift. The reds are less uplift. So this is like a one-story building. If you increase the height of it, you see more blue, and it's extending further from the edge. And as you keep increasing, you see that. So what happens is as you get to a larger and larger building, the pressures get bigger and bigger and bigger. Okay? And these are things that you maybe don't think about every day. So a two-story house is far more vulnerable than a one-story house. I said earlier that it's probably harder to analyze structurally a wood frame house than it would be a steel high-rise building. And the reason for that is it's complicated. We use wood, which has highly variable properties. They have knots, they're cut in different shapes, they dry out differently. If you talk to a builder, they'll tell you that, well, for the same plan dimensions, the studs aren't going to be the same. So if you have an identical house to your neighbors, the inside of the walls could be different. So they're built without those engineering controls, I'd like to say. You have humans putting nails in, so nails don't always get work. Have you watched guys roofing? You know, when you watch them roofing and you think, oh, they're putting a lot of nails in there, that gets pretty boring. Okay, are they really hitting all the spots? So it's tough. Then on top of that, things like your drywall and the cornices in the corner of your roof inside can make a difference structurally. They can make your houses stronger. Okay, but these kind of materials are really hard to analyze. And when you have so many structural members so close together, it's really, really difficult to analyze these. On top of that, houses aren't really designed from an engineering point of view. They've been built through history, so they have a long history, a lot of tradition associated with them. We like the way certain styles look, right? Not for their engineering features, but because they fit historically with different areas. And so we have this process of really, let's hold the roof up so it doesn't fall down on us. Let's keep the weather out. I mean, that's the purpose of the walls, right? We're really happy on the rainy day we had yesterday that we have a roof and a walls because it keeps the rain out. And in the cold of winter, we're nice and warm inside with our furnaces. So the purpose is that environmental control. And so we have these issues that we're trying to deal with. So to actually analyze how these structures behave, to understand how they work, we need to actually test them. And so we built a lab called the Three Little Pigs Project. I talked about the big bad wolf before. And so we developed the project. We called it Three Little Pigs because I think most people here have heard that story and know about it and understand what one's trying to accomplish when we say it's the Three Little Pigs Project. We're going to huff and puff and blow it down. And so we test structures there. There's been work done on houses in Australia. They had a massive hurricane which destroyed the city of Darwin. Can't remember the year now. 1974, I want to say, and it destroyed the city of Darwin on Christmas Eve. And so they started testing for houses and testing wind loads early on. And what they did was they basically Well, what do you want to do? Let's get a big, huge weight and pull on it and lift up the roof and see what kind of capacity it had. And they were able to understand a lot of things. It's not particularly realistic, and so the engineering solutions that arise from that cost quite a bit of money. So we wanted something that was more efficient. So we developed something a little bit different. This is what we're doing at the Three-Little Pigs. So I've talked about the wind. You can imagine the wind blowing, turning the house upside down with the weights, wanting to pull the roof off. What we want to do is replicate those effects. And you could do a couple things. You could build an enormous wind tunnel. They've actually just built one in the United States, in South Carolina, in the middle of nowhere. And it can blow winds 120 miles an hour, and you can test a full 2-story house in that. It costs $35 million to do. And they made a mistake. I was there a few months ago, and they ran the wind tunnel at full power for 45 minutes by mistake because an engineer was doing something. You know what the electrical bill for that was? $75,000. So it's not cost effective for university researchers. So what we did was something that's quite a bit more efficient. So we just want to replicate the pressures. So when the wind blows over, it creates pressures. So how do we create pressures? Well, we do this every day. Well, maybe not every day, but we can vacuum our houses, say once a week or once a month or once a season, right? But when you want to pick up that pesky rock, what do? You put your hose down over the carpet and you get a nice pressure and it lifts the rock up. That's the concept of pressure loading. Okay, that's what the wind does. And so we built a fancy vacuum cleaner. In fact, we didn't here. This is our first version. It's a shop vac. It's a 3/4 inch piece of plywood. Here's a garbage bag. And this is the shop vac bends that plywood substantially. That's the concept. Okay, what we have to add to that then is a way of fluctuating the pressures very rapidly like the real wind does. And so we spent $2 million making a really fancy vacuum cleaner. I think that's more than Dyson spent on his. And this is what we developed. And this device is able to capture all those fluctuations in the turbulence in the wind. We spent $2 million developing that, and then we built 100 of them for another $2 million. So we spent $4 million on that. And now we can test a full house. And when we run our full house, instead of spending $75,000 for 45 minutes of power, we can run for several weeks on a few $1,000s. So it's much more efficient. So what I want to do now is just talk a little bit about that testing. We have a device now that's able, really for the first time, to actually repeatably test houses. And I'm going to start just first with the nails. So how do we test nails? So we can take one of our vacuum cleaners. We call them pressure loading actuators because a fancy title helps us get grant money. And then, so we basically are using that. This is our airbag. We have a fancy airbag. It's not just a garbage bag anymore. And down here we have a toenail connection showing here, and we can actually measure the capacity. We can run our windstorm. So these are our pressures. This is about 45 minutes of a hurricane, let's say, and you can see how the wind load's increasing. We can see how our nail responds to that. So this is displacement versus time. Again, this is about 45 minutes of data, and this is in millimeters. So up here, the nail pulls out at about 10 millimeters, and you can see how it behaves. And one of the things that we learned was, in the wind, there's these large gusts. I showed that before. So there's these gusts, and it's these gusts that cause damage. But interestingly, when you get the gust that causes the damage that we think would want to pull it out, it only pulls the nail out a little bit of the way. So the nails take increments. So in hurricanes, it actually takes quite a duration to pull a whole roof off. This is one of the first things we figured out. We didn't know that before. We would have thought the first time we hit the capacity, it's gone. No, it takes time for that to happen. So that's a single connection. This is the house that we tested, built by our Fanshawe College students. It's a 2-story house. You're seeing it here outside. This is what we call our hangar building, our labs out at London Airport. And the lab, this building here, is actually on rails. You can see the large door. We open that door, and we can slide the building and cover the house, or in this case, uncover it. So we could do, our plans were to cause some damage to the house and then let it sit out all winter and see how much rain gets in through the cracks and things that we caused from damage. Then looking underneath, here's the soffits. The soffits are removed so you can see the top cord of the trusses, and we basically are measuring how the roof is lifting up. We had 60 vacuum cleaners on the roof. This is what the experiment looked like. My doctoral student Murray is sitting here. Here's the ridge of the house, and here's all the vacuum cleaners. So one of the downsides with our method is when you come and look at the house while we're testing, you can't actually see that there's a house underneath there, okay? But when we run these things, it's also very loud. It's, I think it was over 130 decibels, which is well above the pain threshold. As we got comfortable with testing, we of course were hearing protection. We had aircraft earmuffs, I guess, and we put the foam ones inside our ears at the same time. But we actually went inside the house while we were running a test, and we could hear the cracking of the roof above that. And we were applying a pretty significant wind speed here. And the roof, we didn't pull the whole roof off here, we were just causing damage, but we could hear the cracking above it. So people that stay in their houses during hurricanes, I could see they have to be absolutely terrified, because it was frightening to be in there and I knew nothing was going to happen. And it's so loud. So you're going to be listening there to that cracking. The noise would be, I think, would be overwhelming. So we broke the house again. We passed the hurricane by it, and eventually we saw this failure in increments. One of the interesting things is, well, each nail takes a whole bunch of time. Each time it moves, it redistributes the load. And so we have to pull out all the nails, obviously, to fail the roof. And that actually helps it last longer than we expected. And so the failure mechanism was very surprising for us. We're still trying to come to grips with it and doing some other experiments to understand how the roofs come off. One of the reasons why we want to know how the roofs come off is we have tornadoes like in Vaughn or in Goderich. We want to actually more accurately calculate the wind speeds or estimate the wind speeds that occurred to cause that damage. This helps Environment Canada because they're looking at the intensity of the tornadoes on their radar, and we can help them on the ground understand that better. But lots of critical infrastructure is also designed for tornadoes. Electrical transmission or electrical grid is like a big tornado net spanning the continent. And so these structures are well designed and they consider tornadoes, but we want to be able to calculate the risk for that a little more accurately. And so part of this work is not just to understand the failures, but is to help get back out on the wind speeds for tornadoes. And with that, we can find mitigation strategies. The tornadoes that happen, an F2 tornado is categorized, one of the categories of an F2 tornado is that a residential house loses its roof. And one of the things that we're discovering here is that we can mitigate that damage probably for a few $100s. Now, there's tornadoes like Eli, which are F5, but we've had one in Canada's history. Okay, 95% of all tornadoes are F2 or less. And so we can mitigate this damage for a few $100s per house. And if we start holding the envelope, hold the roof on, hold the sheathing on, there's a lot less damage than from debris, and we can save lives, I believe, and also save our infrastructure. And this isn't the solution that I recommend. This is in Spain. I talked earlier I was in Spain. You see this all the time. It has the real advantage of being cheap, but I don't know. I'm not sure that works here architecturally. Well, in the last couple minutes, I want to talk about something a little bit different. Wind energy is in the news a lot. We don't want wind farms next to our houses because it lowers our property values and perhaps makes us sick. There's also real engineering challenges with wind farms, and so we're working on those aspects outside of the political spectrum, hopefully. One of the problems with wind farms is that they're underperforming. So if you're investing in a wind farm, you'll really care about this, because when they make the estimates and they do the economic analysis to make a wind farm, all of those estimates are overestimating the amount of power coming out. And there's several reasons for this, and there's some real challenges for this. Siting the wind farm, terrain effects, so we have topography and hills make a big difference, and the way the farms are set up. A windmill is designed to take energy out of the wind. So every windmill downstream is in less wind. And so how does one model that? And it's quite a complex problem. So we need novel ways of dealing with this. So terrain, again, I wanted to have a photograph of Professor Davenport. Again, this is in our wind tunnel. But you can see topography here from different mountains. There's a bridge here. It's this kind of terrain. Lakes and oceans are, of course, very smooth. Coastal areas have high wind because we have such smooth surfaces around them. As we get into rougher terrain, a lot of the energy of the wind is dissipated, and we have a lot of kind of bad energy of the wind in terms of turbulence, which is bad for wind turbines. That makes it challenging. This should show pretty clearly the problem with wake effects. So you have a turbine here, it's taking energy out of the wind, and it's also spinning what's left going through. And so the ones downstream are in the spinning flow environment of low wind, and that's very, very complex to analyze. And so one of my colleagues, Horia Hangen, and 10 of us from Western put together a proposal, and we got this $24 million, which is really an absurdly large amount of money, to make what we're calling the windy dome. The 3 E's are for energy, environment, and engineering. So the wind, engineering, energy, and environment dome. The size of this, just to give you a sense of scale, is 25 meters across, which is really quite a large wind tunnel. And there's going to be about 120 fans around the periphery and some very large fans around the roof. So we can actually create a tornado in this facility that's going to be about 4 meters in diameter, which means we can do scale model testing of houses. Okay, that's a pretty big tornado, largest that's ever been done in a lab. But we can also look at topography effects on wind turbines, and it's big enough here that we can put cross sections of turbine blades in and study that. And so this is the kind of thing that we're doing next. And I'm going to leave with a nice picture of the wind. All right. So I hope I didn't frighten you. I think there's a lot of things that we can do to mitigate effects of wind. The probability of your house being hit in the City of London is probably once in 10,000 years. We do have 12 tornadoes on average in Ontario every year, and so people do get hit. But for individual houses, it's not so much. Okay, so we have to balance that risk, and that's one of the things that we're trying to do is, what is the risk of this happening? There's high consequences when it happens. How can we possibly mitigate it so that as a society, when there's a disaster, we pay for what's happening in Goderich, the rebuilding, through our taxes. And so how as a society do we mitigate that damage? And so we believe we can influence the building codes. And if we put all of these measures in place, with the number of houses that get built, the incremental cost is going to be practically zero, I believe. And so I think this is something that we should need to try to do, but it needs everyone really to think about it. And the problem is, it's the stuff that makes your house safer is hidden behind the drywall, and you don't see it every day. But I'll stop there and open the floor to any questions there may be.